Hi guys, this is Mrs. Gastler, and in this video we're going to talk about Newton's law of universal gravitation, which I don't want to write out again, so I'm going to call it LUG when I write it out from now on. Okay, so we're going to get started here. I've got some things pre-written, so if you need to stop and pause the video to write it down, go ahead. So we're going to start with what Newton's law of universal gravitation says. And it says that, first off, the force of gravity is between any two masses. So if you have two things that have mass, there is a force of gravity between them. It is directly proportional to both masses. So both masses are going to be in the formula. It is inversely proportional to the square of the distance between the centers. Okay. And so in an equation, what that looks like is this: Fg equals, there's a constant that looks like a giant G, a big G, capital G, m1 times m2 over distance squared. Okay. If you have taken chemistry and you learned anything about Coulomb's law from your chemistry teacher, you might have seen that Fe, the electric force between two charged particles, is K times Q1, Q2 over R squared, which is a very similar thing. There's a fun meme about how Coulomb cheated off of Newton in that one, which is fun. So let's talk about G and D. The distance, just a second note, it is between the centers. Okay, so here we are on Earth. So here's Earth and here is you. To measure this distance, even though you're on the surface, we still have to measure it right there. Okay, so that would be the distance right there, even though it's on the inside of Earth. Okay, and G is what's called the universal gravitational constant, and it has a known value. It's on the equation sheet on the back right here, universal gravitational constant, and it is 6.67 times 10 to the minus 11 newtons per kilogram, no, Newton meters squared per kilogram squared. Okay. And the reason it's Newton meters squared per kilogram squared is so that the meters cancel out, and so that the kilograms cancel out, and so that your final gravitational force is in newtons. Okay. So that is the value there. It's got this times 10 to the minus 11, which is really fascinating because it is a very small number. Okay. So how we figured out and measured G, this is actually really fascinating. Okay, so this Newton guy, right? He just did some measuring, and he figured out really that M1 and M2 both played a role in the force, and that the distance played a role in the force, but I don't think he was able to measure the gravitational constant at the time, although he might have been able to. Later on, this guy named Cavendish, he developed this experiment here where he had a stick with some spheres hanging on the end of the stick, like they were balanced. Okay, so imagine this is horizontal, hanging down, and then he had these two large, probably lead, okay, spheres sitting aside, and he just waited for a really long time, and these things rotated because they were attracted by gravitational forces. So imagine some little force vectors here, and these things are pulling too. There's a force there, but these guys are sitting and they're stationary, and it probably took a good 30 minutes, okay, for those things to move. I've actually done this experiment, but it's really sensitive. Okay, wind, static electricity will keep this thing from moving because the forces of gravity are very small in comparison. There's some other fundamental forces. Gravity is one of them. I didn't write this down yet. Fundamental forces, I think we've talked about these a long time ago. There's 4. 1, 2, 3, 4. Gravity is one of them. Electricity, electromagnetism. It turns out electricity and magnetism are two sides of the same thing. And then there's nuclear, the strong nuclear force and the weak nuclear force. These are the 4 fundamental forces. As far as the range goes, this one can reach really far, and these are all short, and these are really, really short. Really, really short, okay? But as far as strength goes, these guys are pretty strong here. All three of these, this is the wimpiest. Gravity is the wimpiest of these forces, but it can reach really far, okay? So it's kind of this weird thing that's going on. And so this can reach really far, but it's really, really wimpy when it comes. So if there's any static electricity here, this guy gets like stopped and he can't rotate any farther. But what they do is they measure the rotation of these spheres, and then since they know that it's gravitational force that is pulling this guy here, they calculate the forces, and then they solve for G to know what that value is. They've actually calculated this value out to like 15 decimal places or 16, maybe 20. I don't remember. You can Google that and find that out. And this is how they've also calculated back to get the mass of Earth. So if they know what mass is pulling on something and how big things are, they can calculate the mass of Earth that way as well. Okay. And if you're curious to know, well, how do they know the radius of Earth? I'll be happy to answer that question for you sometime too. Okay. That is a geometry question. Okay, so moving from there, let's talk about the M for masses. Okay, so remember, we've talked about mass before. Mass is a measure of inertia, which tells you how stubborn an object is. Remember, inertia is a resistance to change. Okay, resistance to change, resistance to acceleration. Objects don't want to accelerate. It's also a measure of how much stuff there is, how many particles, how much matter there is in an object. Which the more stuff there is, the more it resists change. Okay. In physics, though, we're going to talk about two types of mass, but really they're the same thing. Okay, and that's important for you to understand. Okay, so there's gravitational mass, which really means that we measured it against gravity. So when you go like this, oh yes, that has mass. Then you have just measured gravitational mass. And then there's inertial mass. Okay, so you would measure, hang on, let me write this down. You would measure gravitational mass in a balance. Okay, so if you've seen these before, right? They've got like a little pan over here, and maybe they've got the little hanging down things over here that tells you how much it is, or maybe you put something else on the other side. Okay, you've done that before. Okay, now inertial mass is when you go, oh yes, that has mass. Okay, so gravitational mass, inertial mass. Okay, you can tell how heavy it is. Oh yes, this has more mass. Oh yes, this has more mass. They're the same thing. Okay. Inertial mass is when you measure it against a net force. So the net force here is me shaking it back and forth. Here the force is gravity. Okay, so it's really just something that's not gravity. It makes it inertial mass, and that's really the only difference. When we measure this, we measure it in something called an inertial balance, which is really this interesting looking device that you bolt to a table, and it's got these two little bars like this, and you wiggle it back and forth. Okay, you put your thing in the pan. There's a pan right here, and then it wiggles, and you measure the amount of wiggling. And the amount of wiggling it does tells you how much mass it has, which is just like going like this. Okay, it's the same kind of thing. So far, inertial mass and gravitational mass have always been shown to be the same value. Okay, and so we have no reason to think that these are actually any different. And really, I think this was just somebody's PhD project that they wanted to yeah, I don't know. I really can't say why these are anything that we had to delineate, but we do, and that's okay. Gravitational mass this way, inertial mass this way. Okay, maybe this is so that astronauts, this is how astronauts would measure mass, and this is how everybody on Earth, okay, would measure mass. Maybe that's it. Maybe that's the difference. I don't know. Okay, moving on. Okay, so when you want to use the law of universal gravitation, a lot of the times what we're going to be doing is we're going to be looking at what happens when blah, blah, blah changes, okay? So for an example, we have two planets, X and Y, they orbit a star. Planet X has 3 times the mass and 3 times the distance than Y does. What is the force of gravity compared to planet Y? So what we're going to do is we're going to start off with that formula, Fg equals m1, m2 over d squared. Okay, now they're both orbiting the same star, so one of these is going to be that star. I'm going to change the one to an s, okay, and this can be x. All right, so and the other one, so we'll call this x, and we'll call this y. So ms and my, so y will be our comparative one. So this is just it, okay? So in terms of y, the star has the same mass, but mx is 3 times my, so I'll put a 3 there, y. And the distance is 3 times, so I'll put a 3 there, like that, okay? And so now what I have to do is I have to get all my numbers outside. So the 3 can come out, so I'll have 3g, ms, my. But my 3 is inside here, so I have to square the distance. So 3 squared is 9, so I have 9, distance squared. And then when I put this 9 over here with this 3, that comes out to be 3 over 9, which is 1/3. So I have 1/3 all of this stuff. And since this is really just that, then I'll have 1/3 of the force on y. So it's 1/3 the gravity on planet y. So all I'm doing is manipulating where those numbers are, okay? Things like that. If you need to see more examples of this, please let me know. Finding how the things change is really important. So knowing that the distance is squared and that it depends on both masses is really important, but you have to know which mass is which, okay? And you kind of can pick whether it's 1 or 2, but when you're talking about orbiting, the star is definitely one of the masses, okay? All right, last thing that we're going to look at is using LUG with the uniform, that's a different U, uniform circular motion. And so really what we're looking at is when the force of gravity is that centripetal force. So, and that's what's happening with the planet, right? So the planet is going around the sun. It's actually not really a circle, but it's pretty close to a circle, so we'll be approximating that for AP Physics 1, okay? So what we're going to do for our example here is we're going to look for an expression for the velocity as it goes around. So the thing that you need to be careful of is knowing which m is the one making the circle, okay? And so when you write this down, and you write your FG, so this is big G, M, labeling it star or planet is going to be useful. So M planet, M star and M planet is useful. And then I'm going to change this distance to the radius because that will be helpful, okay? And then over here, it's the planet that's going around, right? Okay, M planet, mv squared over r, okay? And already you might be able to see what's going to happen here, right? I'm going to switch to a different here. So one of these r's is going to cancel out. Isn't that handy? And then my mass of the planet is going to cancel out. So I've got g and mass of the star over r over here, and then v squared over here. And then all I have to do is take the square root of both of those. Okay, so v equals the square root of big G, mass of the sun over r. So does the velocity depend? Can you see that? Does the velocity depend on the mass of the planet? No. So if I had a tiny planet and a big giant planet at the same distance traveling around some star, they would be going the same speed because it doesn't matter how massive they are, the mass falls out of the formula, okay? So that's an application of using the law of universal gravitation with uniform circular motion, okay? So if you have any questions, make sure you ask your teacher. Thanks for watching.